Finally, let's learn how to do matrix multiplication in R. We're just going to add a few things to our toolbox here, and here they are. In order to do matrix multiplication, we're going to use the same sort of nutty syntax that we used for matrix vector multiplication, which was this percent, splat, percent, all three characters all in a row, no spaces. And that was how we took a matrix and multiplied it by a vector last time. This time we're going to do a matrix times a matrix, use the same notation. By the way, as I think I mentioned, if you just put a splat here, it will multiply two matrices together if they are the same size, but it doesn't do it in the mathematical sense. All it does is take each entry of A and multiply it by the corresponding entry of B, which sometimes is useful if you're writing a program and it turns out you need to do that to sort of do some bookkeeping, but that is not matrix multiplication in the sense that linear algebra defines it, right? The inverse of a matrix is computed by using this somewhat weirdly named solve function. So if you say solve and give it a matrix here, it gives you the inverse. That's only for square matrices. And again, if it's singular and doesn't have an inverse, then when you do this solve command, it's going to end up giving you an error, which we'll see in a minute. And then one other thing I'll mention here is there's another way to use the solve command, and this is going to make it more clear why it's called solve, because we can use it to solve a system of simultaneous equations. So if we have one of those systems of equations like we saw last time, and we have it set up in matrix vector form, right? I'm not sure why they use B, but B is the vector that is the right-hand sides of all those equations, and A is the matrix of coefficients. So one way to solve this, of course, as we've seen, is you can take the inverse of A and then multiply both sides of this equation by the inverse of A on the left. And then that will give you the answer, right? The inverse of A times B gives you the answer that that X is going to be, which is the vector of variables that you have. Turns out, though, that it's better to use that second form and to give solve both the matrix and the vector explicitly for two reasons. One is it's a lot faster, which doesn't matter if you're doing 3 equations, 3 unknowns, but if you're doing 3 million equations, 3 million unknowns, you want it to be fast. And what happens is when you use that second form, R, instead of using the inverse explicitly, is going to use this different method called Gauss-Jordan elimination in order to solve the equations. And it turns out that that is a much quicker way and also a much more numerically accurate way of solving a system of equations. You're going to get less round-off error, as we see. Okay? So if you're actually using the inverse to solve simultaneous equations, you don't want to compute the inverse and then multiply that by B. Instead, you want to give them both to the solve function and have it go to work. The reason I teach you inverse is because inverse is used for a lot of different other things besides just solving simultaneous equations, as we'll see in coming episodes. All right? So let's get started here. Let's go to R. We're going to make some matrices here. And just to be fun, I'm going to make them random. So let's make a random 2 by 2 matrix here. We'll multiply by 20 and subtract 10 from each entry. And that is going to give us a matrix like that. Just so it's a little bit easier on the eyes, we'll go ahead and truncate these entries down so that they're integers. So that's our A. Let's make another one, same formula here, get some different random numbers for B. And then I'm going to do one that's C, but I'm going to make it a little bigger. I'm going to make it 2 by 5 instead of 2 by 2. So now C looks like this, right? All right, so first thing to realize is, again, if that's A and that's B, and you do A splat B, that gives you the element by element multiplication, right? So 8 times -5 is -40, and 2 by 3 is 6, etc., right? That is not matrix multiplication the way we mean it. In order to do that, you have to do this nutty operator here, and you get back -38, 30, 27, 9, and I'll let you verify that that is, in fact, this top row, -5, 3, I'm sorry, this top row, 8, 2, dot producted with this first column, which is -5, 1. That will give you the -38, and etc., etc., right? And just to verify what we already know, which is a little bit of a pitfall, if you're not used to it, is that B times A, rather, is not the same thing, right? So we get two very different answers for A times B and B times A here, and that's because matrix multiplication is not, N-O-T, not commutative. Let's do some other things here. Let's take A times C, That's certainly something we can do. However, we cannot do C times A, and that's because C was a 5 by 2, or 2 by 5 rather, right? And a 2 by 5 we can't multiply by a 2 by 2, and this red error message here is R's way of saying, whoa, those are the wrong size. You aren't able to multiply those together. We could, of course, take the transpose of C and then multiply it by A. That would work just fine, because taking the transpose of C gives us a 5 by 2, and that's perfectly fine to multiply by a 2 by 2. Next, let's verify that these things are associative, as we said, right? So remember, this is A, this is B, this is C. If we do A times B and then times C, we get back that matrix right there. And that is A times B, which we've already seen, and then times C. Now the question is, what do we do if we take A times, and then we do B times C right there in parentheses? And the answer turns out we get the same thing. And so B, times C is that hellacious thing. And you never would guess maybe that if you multiply A by that, you get the same answer, but you do. And so this again shows that if we have three matrices we're multiplying together, it doesn't matter what order we do the operations in. It matters very much what order the operands are in. So we have to have A and then B and then C. But doing the A times B part and then multiplying by C gives us the same answer as doing the B times C part and then pre-multiplying by A. All right, let's do some inner product, outer product here. So I'm going to say we've got D, and let's set that equal to a matrix, and we'll make it, we'll do another random one just for fun. We'll make that, how about 7 long times 20 minus 10. And we'll say n row equals 1. So D is a really long row vector there. And then we'll do the same thing with E, except we'll make E be 7 tall. So E is a tall column vector, right? So remember, D times E is simply a number. It's simply the dot product of those two vectors, also known as the inner product. Whereas if I say E times D, whoa, we get this totally different thing, right? And this is a matrix basically giving us every single combination of an element from D times an element from E. It's sort of a multiplication table, as it were. And in fact, we could do that, right? We could say, if we let D be a matrix of the sequence from 1 to 7, and we want that to be 1 row long. And then we said, let's let E be a matrix from 1 to 7, but make it 7 rows long, right? Then if we said D times E, we get that answer. But if we say E times D, the outer product, we actually get a multiplication table. So if you wanted to look up, oh, what is 7 times 6? I never can remember that one. Oh, you could look at it in this table, right? Fun fact. All right, lastly, there's the simultaneous equation thing. So remember we had this example where we said, let's say we've got 3 equations, 3 unknowns. Here are my 3 equations, 6x plus 2y minus 4z equals negative 4, and x plus y plus 2z equals 8, and 2x minus 2y plus 8z equals 4. So remember, one way to solve this is to cast it in matrix vector multiplication form, right? Where A is going to be this matrix of coefficients, which is 6, 2, negative 4, 1, 1, 2. Remember, if you have any missing ones, you got to make sure that you put the 0 in the right place, right? So that's just 6 goes there, and 2 goes there, etc. And then we make this B be the vector form, negative 4, 8, 4. And so again, one way to solve this is to say, let's multiply this by A inverse on the left, multiply this by A inverse on the left. These two things cancel into the identity matrix, and then we've got our answer, bada boom, bada boom. So let's just verify that that works. Let's set our A equal to a matrix with the following entries: 6, 2, negative 4, 1, 1, 2, 2, negative 2, 8. And we'll say that's 3 long, and we have to say by row equals true since we're specifying ones that we actually care about in a certain order. And then let's make our B, and we'll set that equal to a matrix which has negative 4, 8, 4, and we'll say the number of rows equals 3. And now, like I said, if we say solve A, that gives us the inverse of A. Now again, I do not think it's important in this class for you to understand how to get from here to here, right? It's okay for that to be a big mystery, I think, how to get the inverse, because that's what computers are good at. What is important to understand is what an inverse is, and to understand that if we take the matrix A and we multiply it by its inverse, we get back the identity matrix. Now, when we look at this, it may not look like the identity matrix is first, because you're like, wait a minute, there's all this negative 4.44, 5.55, right? I thought an identity matrix was just ones on the diagonal and zeros everywhere else. True dat. But here's the thing, that is actually what we have. If you look at this, it's expressing each of the entries here in scientific notation. And this e to the plus 0, 0 means times 10 to the 0. And this e to the minus 17 means times 10 to the negative 17th. So this entry right here, this negative 1.38 thing times 10 to the negative 17th, what that really is negative 1.38777. But I'm going to move the decimal point over 17 times, right? So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. That's really what that number is there at row 2, column 1, which is pretty darn close to 0, I think you'd agree, okay? So this is round off error that we get when we do the inverse, and that's why it doesn't come out exactly right. It comes out to be very, very, very close to right. And in fact, if it bothers us, we could go ahead and round that. Let's, round this thing to, 5 decimal places or whatever. And then we do, in fact, get the identity matrix, and it's obvious that's what it is. Okay? So, to solve this, equate to these simultaneous equations, we're going to say, get the inverse, and then multiply it by b. And negative 1, 5, 2, if you recall, that is, in fact, the one and only solution to this thing right here. X equals negative 1, y equals 5, z equals 2. If you plug it in, you'll find out that all 3 equations are satisfied, and there actually is no other pair or no other triple of numbers that will satisfy that. Again, sort of the better way to do it in terms of round-off error and speed is to do this in R, is to give both those to R and say, hey, do Gauss-Jordan elimination to find the solution to these simultaneous equations, and you can see you get back the same answer here, right? All right. So last thing, and that's just what happens when we have a singular matrix, right? And we know that it doesn't have an inverse, so what's going to happen is solve is going to break. And here's what it's going to look like when it breaks. Let's take my A here. Let's go back to where we defined this. And what I'm going to do is I'm going to change the last row. I'm going to set the last row to 7, 3, negative 2. Now you might wonder why I chose those values, and the reason is because what I did was add the first row to the second row, and then I made just the third row be the sum of those two, right? So 6 plus 1 is 7, 2 plus 1 is 3, negative 4 plus 2 is negative 2. Since I did that, that tells you that these rows are not all linearly independent, right? Because you can get the third one from the first two. And we know that if it's not full rank in terms of the rows, it's also not full rank in terms of the columns. So I do not have 3 linearly independent columns anymore. So I can tell you right now, it's going to be singular, and let's see what happens when we try to do this. Hey, what's the inverse? It comes back and it says, whoa, this is computationally singular, which means it is so close to being singular, which really it is exactly singular, but when R goes about trying to figure out the inverse, it says, you know what? I tried to figure out the inverse to this thing, and I couldn't find one. And that tells me, really, that it's computationally singular. And that's basically the rule of the game, right? If there is a matrix that's not full rank, if there's a matrix that does not have all linearly independent columns, then that thing is singular and cannot be inverted, and R is going to throw a flag at us and tell us that that is in fact the case. And we know that you can't solve those simultaneous similar equations when that is the case. All right, matrix multiplication in a nutshell. I will catch you next time on All the Math.